Good morning, everybody. In today's session, we'll continue with the third type of CD work, that is, first level crossing, another one is inlet and outlet. Here, first, we'll see what is level crossing. Here, in this type of cross drainage work, the canal water and the drain water are allowed to intermingle with each other. Here, a level crossing is generally provided when a large canal and huge drainage, such like stream or else river, etc., in approach of each other practically at the same level. So here they are going to mingle up with the same level, and a regulator is being provided across the drainage just on the downstream side of the crossing so as to control the discharge passing into the drainage. Let me show that one in a diagram. See, here you can see this is your river, this is a drainage, and this one is the canal, and here we are going to provide a regulator so that the water can be discharged whenever we want. That is, we are going to control the discharge passing into the drainage. Here at the outgoing of the canal, a regulator is also provided so as to control the discharge into the canals. Here in this arrangement, a perennial drainage discharge is sometimes advantageous, used so as to augment the canal supplies. Here what happens in this level crossing during a dry season, when there is no floods, the drainage regulator is generally kept closed and the outgoing canal regulator is kept fully open, so that the canal flows without interruptions during the flood. However, the drainage regulator is opened so as to pass the flood discharge. This is about level crossing, and next we'll go for inlet and outlets. So here an inlet is a structure constructed in order to allow the drainage water to enter the canal and get mixed with the canal water, and thus to help in augmenting canal supplies. Here such a structure is generally adopted when the drainage discharge is small and drainage crosses the canal with its bed level, which is equal to or slightly higher than the canal FSL, that is full supply level. Thus, in an inlet, the drainage water is simply allowed to the canal. But when the drainage discharge is higher, or if the canal is small so that the canal section cannot take the entire drainage water, an outlet may sometimes be constructed to escape out the additional discharge at the suitable site. A little drainage discharge in the downstream along the canal. Here an inlet eventually consisting of an open cut in an canal bank, suitably protected with pitching, and admit drainage water into canal. The bed and sides of the canal are also pitched for a certain distance of upstream side as well as the downstream of an inlet. Similarly, the outlet is another open cut in a canal with bed and sides of the cut properly pitched, and the escaping water from the outlet is taken away by a lead channel to some nearby drains on the downstream side of the outlet. Here you can see this is an inlet and this is a leading channel. This is a stream, and outlet is going to give a direction, or you can say that like the water is being diverted from this way to another way where the leading channel is going. This is about outlet and then inlet. Okay, next we'll go for various types of aqueducts and siphon aqueduct. Here in this type of sides of an aqueduct are earthen bank which completes earthen slopes, and the original canal section is retained. Thus in this case the length of the culvert or barrel which the drain water is passed under the canal must be sufficient not only to carry the water section but also to carry the earthen banks of the canal with their slopes. Here in this diagram you can see, might be it is bit blur. See, this is your canal and this is road, and this two are the earthen banks, and this is a drain and this is a culvert. Okay, next we'll go for type 2. So in this type the canal continues in its earthen section over discharge drainage, but the outer slope, here the outer slope of the canal banks are replaced by retaining wall. You can see over here these are the retaining walls, but thereby the reducing the length of the culvert barrels by that extent. So this is about this type 2. Let me repeat the same thing. In the type 1 the earthen bunds is provided, and in the case of type 2, here at the outer slope of the canal we are going to provide a retaining wall. Thus we are going to reduce the culvert barrels. Okay, next we move on for the type 3. So here in this type the earthen section of the canal is discontinued and the canal water is carried in a masonry or a concrete trough. So this is your drain and here this is your canal. Okay, here there is no earthen bund over here. You can see there is no earthen bund. This is road and this is canal, and this is your full supply level, and this is high flood level of the natural drain. The canal is generally flumed in this case so as to affect economy in construction. Thus in this case the length of the drain culvert and the barrel is considerably reduced compared to other two types of aqueducts and siphon aqueducts. Now next we'll go for contraction of canal waterways or fluming. What exactly this is? Okay, here in the case of type 3 aqueduct the canal is flumed. That is the meaning of flumed is the canal waterway is contracted to economize the cost of drainage work, that is CD works. Okay, the flumed portion or the trough is generally connected to the normal section with smooth transition wings at both the ends. So here what happens, the contraction of the canal waterways although reduces the barrel length or the width of works, but it involves the provision of extra transition wings. Here the fluming or the contraction of the canal waterways should be done in such a way that the velocity in the trough is not more than 3 meter per second and the flow remains in subcritical condition. So here what the subcritical condition means, in turn we are avoiding the possibility of hydraulic jump formation in the trough. Okay, the approach or contraction transition should not be steeper than 30 degree, which corresponds to a slopes of 2:1, and the expansion transition should not be steeper than 2, that is 22.5 degree, which corresponds to the slopes of 3:1. The transition consists of curved and flumed wing walls so that there is minimum loss of head and the flow is streamlined. So the question is how we are going to design these transitions. Here they can be designed in two different conditions consideration. One is the design of transition when the water that remains constant. Another one is design of transition when the water depth varies. First we'll go for first design, that is when we are going to consider the water is remaining constant. So here first thing, the design of this transition when the water depth remains constant can be done following two methods. One is Mitra's hyperbolic transitions. Another one is Chaturvedi's semi-cubical parabolic transition. Only thing is there is a small equation variation. Okay, see here whatever I have explained you over here, you can see the contraction transition is having an angle of 30 degree, that is in turn the slope is going to be 2:1. The first point what I have explained you for this fluming. Okay, and another point what I have explained you at the expansion transition, the angle is going to be 22.5 degree, that is the slope is going to be 3:1. Okay, so here this is the flumed section, and this one overall it was before it was the actual width, but after fluming that base width is being reduced, you can see. So directly we cannot reduce, that's why we go for transition. This is what I have explained you in the type 3. Okay, and what we have got to know about this using the contraction and of canal waterways or nothing but fluming. Okay, so here let me erase this one. Okay, here first thing, this is your contraction transition and this is your expansion transitions, which are the two extra transitions which is going to come to reduce the width of the canal, but the length will be large enough. Okay, then we'll see what are the some of the assumptions what we are going to do to get into a equation for the design of transition when the water depth remains constant. Okay, so Bn is nothing but the bed width of the normal section, and Bf is the bed width of flumed section. Here another one is the transitions. In this one we are going to consider Bx, that is the bed width of the transition from the flumed section. At this section is a flumed section, okay, this second and third, this is a separate flumed section, and from there this 2 to 1, this one is a transition section, and from 3 to 4 it is a transition section, okay. So Bx is an transition base width of the transition section from the flumed section, and this is we are going to consider at some distance. So that distance I'll consider it as x distance from the section 2, okay. And in the meanwhile, the velocities over here at the Bn, that is a normal section, and Bf and Bx, at these three sections the velocities we can make it as Vn, Vx and Vf, and this one total length, it will be Lf, that is the total length of transition, okay. Next, the transition is designed on the basis of that the rate of change of velocity per unit length of transition is constant throughout the length of transition. So what happens here, the velocities from the flumed minus Vx divided by overall distance, how much it is moving. So divided by x is equal to Vf minus Vn divided by overall distance from the flume length, okay. That will give you the rate of change of velocity per unit length of transition, okay. So here you can see Vf minus Vx divided by x is equal to Vf minus Vn divided by Lf. So we'll consider that one as equation 1. Now here the depth, what we are going to assume is y, and it is to be constant because the water is being constant, okay. So the total discharge Q is also constant, because if the depth is constant, definitely the area will be constant, and velocity is going to be vary, but the discharge will remain same because of the depth, okay. So definitely the velocity V into A is nothing but the width into depth, correct? So here for the flume section, the discharge is equal to Qf, and for the X section, that is transition section, the discharge will be Qx. Here I'll write Qf, and this one is Qx and Qn for the normal section. This overall will become equal to Q, that is a normal discharge, and it is constant. Here Qf, I want to calculate what is Qf. Qf is nothing but area into velocity. Area is base into depth. So base width is how much? Bf into depth is y, that is constant. Y into velocity is Vf, that is what over here I have written. Vf is equal to Bf into y, and for the transition section the discharge will be Vx into Bx into y, and for the normal section it is Vx into Bx into y. So overall it is equal to the constant Q. So I'll take out y as common out of these. So here it will be Vf Bf is equal to Vx Bx is equal to Vn Bn, and I'll take this one as into the denominator. So it will be Q divided by y. I'll consider this one as K, some constant K value, okay. Now if I want the velocities for each section, so I need to equate that to k value. Okay, then you'll be getting what is the velocities at each section. So definitely it will be Vf into Bf is equal to k. So using this one we'll get what is Vf, that is Vf is equal to k divided by Bf, and Vx is equal to k divided by Bx, and Vn is equal to k divided by Bn. So we'll consider this one in as equation 2. Now using the values of Vf, Vx and Vn, we are going to substitute this one into the equation 1. So your equation will be this. In this one equation, we'll take out k as common, and overall the final equation will be, after solving, I'm not going to solve it, just while you're practicing, just solve it off. Okay, final your equation will be Bx is equal to Bn Bf Lf divided by Lf into Bn minus x into Bn minus Bf. So Bf is what? The base width of the transition section at a distance of x from the flumed section. Okay. Now since we are done with the one part, that is a design of transition considering water depth as constant, now we'll go for another type, that is Chaturvedi's semi-cubical parabolic section for the same design of transition considering the water which is going to be remained constant. Okay, here it is given by an equation x is equal to Lf Bn to the power of 3 by 2 divided by Bn to the power of 3 by 2 minus Bf to the power of 3 by 2 into 1 minus Bf divided by Bx to the power of 3 by 2. This was given by continuous investigation and experimentation, and finally he proposed this equation and choosing the convenient walls of Bx, that is transition base width, and considering the distance x, be computed from an equation. Okay, this is about the design of transition when the water depth is constant. Next we go for design of transition when the water depth varies. Okay, here it is being done using Hind's method. In this design of transition, there are 9 steps to be carried out to design this transition. Transition means like this whole thing. If I want to design whole thing, there are 9 steps to be followed for the design of this transition as well as design of aqueduct. So today we'll stop over here, and tomorrow's session will continue the design of this transition with a varying water depth. Okay, in today's session the question is, what should be the flow condition of the canal waterway to avoid the hydraulic jump?